let's do this. Let me say a couple of words about the first homework. It's due a week from today. Okay, so you can assume that all rings have identity. In fact, unless I tell you otherwise, you can assume they're commutative. And that all modules are unitary. The first one, show that R is a commutative ring with identity, and M is an R module. Show that as R modules, there's an isomorphism from homar, Rm, and M. So recall what this means. M is an R module, and R is, of course, an R module over itself, right? So the homomorphism from R into M, R module homomorphism, isomorphic to M. That's kind of that'll be useful, and we'll use this later in the course as well. Number two, suppose R is commutative with identity, and M is an R module, and little m is just some random element in M. Show that I sub M, which is all the crap in R that kills M, right? It's everything that turns M into zero if you multiply. Show that this is an ideal of R. So here's a little terminology. If I sub M is not zero, we say that M is a torsion element of M. B, if R is a domain, show the set of torsion elements of M forms a submodule of M. And show that if R is not a domain, this may not be the case, right? So that's kind of an important one right there.
What do you mean by domain here?
An integral domain. So commutative ring with identity that has no non-zero zero divisors. Number three, suppose F from A to B is an R module homomorphism. Show that F is an isomorphism if and only if there's an R module homomorphism going in the other direction from B to A, such that the composition in both directions appropriately is the identity on B and the identity on A. So this 1A means the identity function on B and A. One of the directions of this is pretty easy. The other direction, you really need to show that what you have is an R module homomorphism. Four is kind of a fun one. I love this one. Suppose, and actually this one comes up in linear algebra quite a bit as well. Suppose you have F from A to A, and suppose F is an idempotent transformation or an idempotent R module homomorphism. And what I mean by that is F of X is F of X. So once you take X and do F of X, repeatedly applying F to it just leaves it alone. Show that A is isomorphic to the kernel of F direct sum the image of F. Right? That's kind of a nifty one. And finally, I think this is pretty easy once you figure it out, but I think this is worthwhile to kind of think about for a minute. Show that there is no unitary Q module structure on Z. Q is a Z module, but Z is not a Q module. There is no unitary Q module structure on Z. So see if you can figure out how this. Okay, any questions? All right, so let's kind of pick up where we left off last time with all right, so the last thing we looked at was 619, basically claiming that you have conditions on what it means to be submodule. Let's go through this. R is ring, M is R module. 619 again. that our submodule only n is well, we've got that, and x plus r y is an n. Okay, so this is sort of like you remember the subgroup criteria, right? From group theory, it's essentially the same thing. So yeah, okay. So suppose that this is in fact an R that n is the left R submodule, then as well. Uh, if x and y are in n and r is in r, then ry is in n, right? Because the fact it's a left R module. Therefore, x is ry. And there you go. So you've got this. Now suppose that for all x, y, and then in R and R, well, okay, to show that this is a submodule, that is to show that it's a submodule, first of all, notice that it's non-empty, right? That's kind of a basic assumption here. And first, notice that if you take R equals -1, then x minus y is in M. And so therefore, subgroup. We've got that taken care of, right? And what else do we need? Well, now all we need to do is to show that it's got that it's such, it's got the vacuum cleaner property, right? So uh, so now let x equal 0 and y be an arbitrary element of M and R be an arbitrary element of R, then 0 plus RY equals RY is in M. And so N is a submodule. Or what's submodule? Yes.
Y is an element of N, right?
I'm sorry?
Y is an element of N.
Yes. I keep doing that, don't I? You're absolutely right. There we go. Okay. Let me give you some good examples of submodules. You've seen this sort of on the homework. Example. Homomorphism. So if I walk up to you on the street and give you an R module homomorphism from A to B, I can pick out a couple of important submodules, right? This is the kernel that you're used to from study abelian groups, say, set of X and A, such that that is 0, is an R submodule of A, and a very important one. So, and the image of that, which is the set F of A, is an R submodule of B.
I need to be subjective for that feature.
No. And in fact, that's, of course, if it is surjective, then the R submodule B will be B itself, right? But let's prove that. And then I'll turn off this phone. All right. First, oh, by the way, let me point out that both of these are non-empty, right? I mean, that was one of the things we talked about, because certainly 0 is in the kernel, right? Because 0 always goes to 0, and certainly the 0 element of B is always in the image. No problem there, right? So let's let X, Y be in the kernel of F. Look at F of X plus R, Y. Well, because this is an R-module homomorphism, I've got that. And because X and Y are both in the kernel, these are both nuked. So this is 0 plus R times 0, which is 0. Therefore, X plus RY is in the kernel of F as well. And there we go. So that means that the kernel is a submodule. Okie dokie so far? For number 2, for the image, let's say WZ be in the image of F and R in R. Now let's dissect what this means. What does it mean for W and Z to be in the image of F? It means there's some crap back here in A that goes to it, right? So there exists A1, A2, and A such that W equals F of A1 and Z equals F of A2. Right? So now let's notice that if you look at W plus RZ, let's look at W using these guys right here. This is F of A1 plus R F of A2. And now I will liberally use the fact that F is an R module homomorphism. Write this that way. Right? Therefore, W plus RZ is in the image of F by definition, because F of this n gives you W plus RZ. So, image of F contained in B is so. Right. And notice, for example, if F is the 0 homomorphism, and by the, of course, I mean the 0 R module homomorphism. I don't usually expect 0 to be a ring homomorphism. This is 0 homomorphism, and the image is 0. So in the case that this is the 0 homomorphism, then image of F would just be 0, which is certainly submodule B, and the kernel of F would be all of A, right, which is submodule of that. And in fact, this, I'll let you prove this kind of yourself because it's an easy generalization of this. more generally, if C is an R submodule, then look at F inverse C. So this is like the analysis kind of thing. It's just the preimage of C. So this is all the stuff. We just look at all the stuff that's back in A that actually lands you down in this submodule is an R submodule. In the special case that C is 0, then F inverse of 0 is the kernel. In the special case that C is all of B, then F inverse of C is just A. Right. Everybody okay with that? Okay, so let me ask you this. Let me have this situation right here. I'm gonna kind of pass this definition here. Okay, so suppose I give you your favorite or your favorite R module A, and then I give you just some set. This can be any subset, no structure to it, just contained in there. Now, by the pointing brackets notation, I mean the subset, or I'm sorry, the submodule generated by that set. So you might now look at X as a set of generators. Anybody, what's a good way to define this? Yes.
Smallest submodule of A containing X.
I agree. I agree with you. Whereas, how do you define smallest? Okay, there you go. Right. Good, good, good. The intersection M so you take every stinking submodule of A that contains that set X and you intersect. And I like this smallest submodule of A. Right, because you intersect every single. Now, one of the things that I probably need to do, if I'm going to be super careful, is to make sure that this actually is a submodule, right? Right, is the intersection. So, note, you might explain why that's true. Yeah.
Well, at least like, the intersection is not empty because it contains text.
Right, every one of these has to contain 0, right?
Eight.
So you've got that. I bet you all learned in 8510 that if you intersect a bunch of groups, it's a subgroup, right? Okay, so at least this thing's got that going for us, right? It's certainly a subgroup. Of him. And now we just have to show that it's closed under multiplication by n, but of course, every one of these submodules is. So if, let's say, z is in x, then z is in m for all submodules. Then for all submodules containing x, say m, z is in m. Well, if you look at RZ, is also in each, so RZ. So this actually is a submodule of M. Let me give you some notations that we'll use here in conjunction with on this. So if X, let's take special setting here. If X is the union of BI's, I in some index set with each BI a submodule of A, then the submodule generated by X is called the sum of BI's. Sometimes we might write X. And if you have a finite index set, then okay, so let me ask you a couple of kind of review questions here. Well, at least for the group theory aspect of this. So in this case where X is the sum of the BI's, what's the difference between just a sum like I've written here and a direct sum? What would it mean for these BI's to be direct? Yes.
Their intersection is trivial.
Right. More than that, each BI intersected with the sum of what's left over is trivial, right? So B1 intersect the sum of what's left over, B2 intersect the sum of what's left over, these are all trivial, right? That's what it would be for the sum to be direct. The direct sum of modules is just like the direct sum of abelian groups. It's just now you've got that extra scale of multiplication. It's essentially no different. Let me ask you another question. What happens here if X is the empty set? Yeah, the universe collapses. No, so what happens if X is the empty set is now what you're doing. Notice every submodule, every set contains the empty set. So what you're now doing is you're intersecting every submodule of A. And so what are you going to get? Zero. You're going to get the zero submodule, right? So oftentimes you'll sometimes hear this said that the zero module is generated by the empty set. It's kind of embarrassing, but I'm going to do this. Here's an important class of module, and it's embarrassing that we're now. Yes.
Sorry, first, can you tell us, is it possible to write generated by X in element form? Are the elements linear combinations?
So let me clarify what this is. This could be an infinite index set, but a typical element here involves only finitely many non-zero things. So these sums are always finite. So the sum of the modules could be infinite, right? But you're not allowed to add more than finitely many non-zero things at a time. Now, I needed to say that, but I don't know if I addressed your question.
Oh, no, thanks for saying that. And I'm wondering if the intersection definition can be rewritten in element form? Like the.
Oh, right. So if what you can do is, so suppose that X is, suppose X is not empty, right? So because empty is silly. Then the working part, so you might verify for yourself it's true. This is the set of all R(x)(1), R1, R2, X(i)(2), RK(x)(k), where Ri is in R and I sub j is in the index set. Right. So in other words, if you write the generating set with the set X down just as a collection of elements, then what's generated by X will be all finite sums, finite linear combinations of stuff that you can pull out. Does that address your question? Yeah. So yeah, show that this is the same thing as that intersection. That's a fun little exercise.
Looks like a sum of principal ideals, right?
Right, but so if your index set is finite, then you've got a finite generate because you can always use the same ones over and over again. If the set is infinite, then it's, but yeah, so certainly you could write it as a sum of principal ideals, right? So it's embarrassing that we're a couple of days into your second semester, and I'm just now going to tell you what an algebra is, an algebra class. What are the unit one? Number one, an R algebra is a ring A with identity we'll call it 1A, equipped with a ring homomorphism, let's say F from R into A, and let me emphasize here that you take the identity of commutative ring with identity of R and the identity of A, such that if you look at the image of your ring R, this is contained. You see that? And the center of A is, as you might guess, it is the collection of everything in the ring A that commutes with everything in the ring, right? Anybody want to take a wild guess? So almost everything in mathematics, almost, what we do is, we tell our kids in the proofs course, it's like, do not give me an example, a proof is not an example, and we beat on them and things like this, right? However, examples are important. In fact, everything in mathematics comes from an example. In fact, most definitions are generalizations of stuff that work really groovy. What do you suppose this is? What do you suppose this definition generalizes? Well, I tend to think of Morpheus and Neo and those folks. This looks very much like generalization of a matrix, right? So take a ring R. Where this is the set of n by n matrices over the ring R. Notice that R is commutative. This ring is never commutative if the n is bigger than 1, right? So if it's 2 by 2 or higher, no chance, right? So what is an R algebra? There's a ring. The matrices form a ring, right? Equipped with a ring homomorphism. How does a homomorphism work?
With diagonal.
All right, there you go. Remember in math, don't do it if it isn't easy. And notice, what do we call these? The scalar matrices, right? Notice those matrices commute with every matrix. So this is in the center of going A. So this is somebody picked out the properties that they thought about matrices that are important, you know, from this perspective, and they generalize this to a more general R algebra. Okay. Let me put this proposition in here that you know, A is an R algebra, then A is an R module. Okay, so let's kind of go through this. Of course, A is an abelian group under addition. Right? A module is first and foremost an abelian group, and A is an abelian group under addition by assumption because A is a ring, right? So it's being an abelian group. Now the question is, how do I define my multiplication? And I'm going to make this actually a two-sided module, right? Right? Because this is R is a commutative ring. I'm going to define let R be an R and let A be an A. And I'm going to define, now I'm claiming that this is an R module, so I've got to be able to do that.
That's a large.
That's right, because at the outset, R and A are just two different animals, right? This is some ring and this is some other ring, right? How do I tie it together? There's a homomorphism that actually pushes R into A. So I can multiply this. I'm going to find this to be F R times A, and I'm going to define this to be A times R as well. Why does this make sense for me to define it both-sided? That is exactly right, because whatever this little animal here is, this F of R in the center of A. So now we've used that to our advantage here. So let's go through this here. One R times A is F of one R A, which is one A, which is A. Okay, excellent. That works on both sides, just by that observation up there. What else do we need? Let R, S, B, and R, A, B, B, and A. Let's see, what do we need? We need R times A plus B. Well, by definition, this is F of R times A plus B. But these F of R now sits in the ring A, as do these, and it's a ring, so it's got the distributive property. So this is F of R, A, plus F of R, B, which is R times A plus R times B. Okay, so that bit of the module stuff works, and it's easy to check that it works on the other side because F of R is in the center. R plus S operating on A. Well, this is by definition F of R plus S operating on A times A. But this is a homomorphism. So this is actually F of R plus F of S times A, which is F of R A plus F of S A, which is R operating on A plus S operating. Okay, so we've got that going for us. And finally, if you look at RS operating on A, by definition, this is RSA. Again, this is a homomorphism. So this is F of R, F of S times A. And I can put the parentheses here. This is F R times this element S dot A, because S dot A is an element of S, or I'm sorry, of A, and this is R. So it is indeed an R module. Okay, any questions? Let me give you one last definition before we start talking about homomorphisms in quotient structure. So now we've got this thing called an R algebra, right? So it's a module over R, but it's something more. It's basically, I think when I try to remember what it's like, again, I think matrix rings. Definitely. Yeah, A and B are algebras. I might want to define an R algebra homomorphism. So what does it mean to be an R module homomorphism may be? Well, I want it first and foremost to be a ring homomorphism because both of these R algebras are in fact rings. This first one is a default assumption that I give to ring homomorphisms, but I put it here for emphasis. My default is all ring homomorphisms fit the identity to the identity. And also, I want this to behave like a ring homomorphism on the elements of A, and I want to be able to factor out the elements of R, right? So I wanted to have that. Remember, we pointed out that this is an R module homomorphism. I want this also to be an R module homomorphism. So it is both a ring homomorphism and an R module homomorphism. Okay. Any questions on that? Okay, so now we're going to talk about quotient structures and the homomorphism theorems. Now, you haven't seen modules before, now you have, but I still hope that this is going to be mostly a review because the theorems I'm going to say are almost in lockstep with the homomorphism theorems you've seen before for groups, for rings, et cetera, et cetera. And in fact, it's good to remember that any R module is first and foremost an abelian group. And so basically, this is all just a big fat copy job of all the group homomorphisms, and you've just got a little extra structure on there, and everything kind of passes through. Let me begin. Following. Here. Term 621. Let B, C, and A be R modules. Quotient group A mod B. So this is an old-fashioned abelian group from the old days, is an R module. So, okay, this is naturally, this is an abelian group, and in fact, it's an R module. For this to be an R module, I've got to have an R action on the set of cosets. So if I have an element of R, and I have the coset A plus capital B, what does this got to be? Ooh, I know. It's got to be a plus B, right? Because it's got to be an R module. What do you suppose belongs here? There you go. Once again with the easy, right? Number two, the map. Yes. Sometimes I call this projection map. Given by V of A gives the coset A plus B. So this is just reducing this mod B. That's it. Is an R module homomorphism. Actually, I'm going to go further than this. What can I say that's probably even more descriptive than just homomorphism? Yeah, right. It's on to, isn't it? Right. With what do you suppose the kernel of this is?
B.
Good. there is an R module homomorphism. Uh, the and finally, uh, four. If in the special case, if C is actually contained in B, then B mod C is contained in A mod C. And what is more, A mod C modulo B mod C is isomorphic to A mod. Okay, so questions on this? Let me kind of take you through this a little bit, not too many details. Really what you need to show here for the first one, we know that A mod B is a quotient group depending on what we've done before. We need to show that this action is well defined, right? So suppose A plus B, A prime. Right, so suppose that you have two different representatives, A and A prime, for the same coset, right? What does this mean? If these cosets are the same, what does it mean about the difference between A and A prime? Right. Therefore, R A minus A prime equals RB, which is in B. So RA minus RA prime is in B. Therefore, RA plus B equals RA prime. Because this difference in B means that these two things represent the same coset. So this multiplication that we find is well defined. Right? This one is, I think number 2 is pretty evident, as a matter of fact. How about this one right here? Actually, I think maybe we'll come back to this and prove both 3 and 4 later after we do the first isomorphism theorem. Because the first isomorphism theorem, as you may remember from groups, is the king of all isomorphism theorems, and all the other ones follow from it. So next time we'll do the first isomorphism theorem and show how, well, remind me if I forget, but we'll show how this connects. Okay, any questions? Well, no math club this week, but it'll start next week, so get juiced up for that. It'll be a lot of fun, and y'all have a good, oh yeah, we've got a long weekend, so y'all have a good weekend and Martin Luther King Day, and we'll see you on Wednesday.